One of the ways that we can display what's happening in a reaction in terms of energy is by drawing a reaction profile or energy level diagram, as they're sometimes called. These are simple diagrams which just show the change in energy. So to start off, I'm just going to show a bar chart of chemical and thermal energy in a system, any system that's happening with a chemical reaction. Now, you may remember that when we have a chemical reaction happening and it's an exothermic reaction, that means it gives out thermal energy as heat. Because it's giving out thermal energy as heat, chemical energy must be changing from chemical energy into heat. Therefore, as the heat energy goes up, the chemical energy goes down. And that would be an exothermic process. Now, the opposite is true for an endothermic reaction. As the surroundings get colder, as the thermal energy goes down, the energy has to have gone into the system as chemical energy, and therefore the chemical energy goes up. Okay, so no energy is lost, it's all conserved, it's just transferred from chemical to thermal. And when we represent this on an energy level diagram, we are plotting reaction progress on the x-axis, and we're plotting the chemical energy on the y-axis. So I've taken an example here. This is methane burning in oxygen, and I've written the reactants there on the left-hand side of that line. And we know that this is an exothermic reaction, it's a combustion reaction. So the expected change is going to be that the thermal energy is going to increase and the chemical energy is going to decrease. We can see that in the bar chart on the right. And as we see that, let's look at what happens to the line on the enthalpy profile diagram. So you can see that we are plotting the chemical energy. Therefore, for an exothermic reaction, the line for the products is lower than the line for the reactants. Let's just expand that and add a bit more detail. So we've done our reaction. We can see that heat is given out, and the second line is lower because we have lost chemical energy. Now there's no thermal energy on here at all on this diagram, okay? And this is where people get confused because people get confused between the temperature rising but the line is going down, and it's important to understand that we're talking about the chemical energy here, not the thermal. So once we've got these two lines, we can measure the distance in between them if we plotted them onto a graph, and that distance would be the energy change of the reaction. Now, it's very important to make sure that you've connected the lines to the arrow, and it's a vertical arrow, there's no gaps in it. And because we started higher than we finished, the arrow is going down. We're going from the first line to the second line. So that's energy change of reaction. And that is an energy level diagram of the reaction between methane and oxygen. Here's another example. This is something you can potentially do in your kitchen. Bicarbonate of soda is sodium hydrogen carbonate, NaHCO3, and vinegar is CH3COOH. And this reaction produces carbon dioxide and water, and also a salt called sodium ethanamate. This is an endothermic reaction, so if we look at the bar chart on the right hand side, we're expecting the thermal energy to come down and we're expecting the chemical energy to go up. And so in our energy profile diagram, or our energy level diagram, we are going to see the line going up as we are gaining chemical energy as the surroundings are getting colder. So once again, what I'm going to do is I'm going to put the products on that second line. I'm going to draw an arrow from the first line to the second line vertically, and this time, because we're going from the first line, which is lower, towards the second line, which is higher, we're going to have that arrow pointing up. Again, there's no gaps there at all. Label that energy change of reaction, and we can tell that this is endothermic because the products are at a higher energy level than the reactants. So, just a quick summary of that. Exothermic reactions lose chemical energy from the system to the surroundings. The product line is always lower than the reactants because we have lost chemical energy as heat to the surroundings. Endothermic reactions, it's the opposite. The product line is always higher because the temperature decreases as the increased chemical energy reduces the heat of the surroundings. So we're taking energy in. There's just one more thing. Something called activation energy is involved as well, and I've shown this on this diagram here as an upwards arrow. What is it? Well, if you take methane and oxygen, if you've ever turned a gas tap on, you'll know that it doesn't immediately explode. You actually need to put a match or a lit splint or something nearby in order to make that reaction happen. You have to put in a little bit of energy to get it to work. And that's what activation energy is. It's the minimum amount of energy we need to put in to start that reaction. So you can see, because I have to put energy in, my blue line is going upwards. And when I get to the point where the reaction starts, it will start coming downwards again. And the activation energy is from the start line, my methane and oxygen, the red line, to the very top of the hump. That is the minimum energy I need to put in to get this reaction to work. With an endothermic reaction, it's the same idea. We still sometimes need to put in a little bit more energy than necessary to get the reaction started. So again, you can see that we start at the red line for the reactants. We go up because we're putting energy in from the red line to the top of the blue hump. That is the activation and energy. And then it will come back down again towards the product line. The energy change of the reaction stays as it was. Okay, it's just this is how much energy we need to put in just to kick-start the reaction. So there's a definition of activation energy. It's the minimum energy required to start a reaction by the breaking of bonds. We always put energy in to do this, and so we always go up to show activation energy with an upwards arrow.